Hello and welcome to Writing Organic Reactions. Um, for organic reactions, there's in a way a lot you need to be able to do, but there are a few skills that are kind of tend to be tested and focused on a little bit more. Identification is huge, which was in the last set of notes that we did. Today's notes will really be looking more at finding out what's missing in a reaction, determining reactants or products in addition, reaction, substitution, and esterification reactions. Again, identity is what we talked about in the last one. The three that we worry the most about are addition, substitution, and esterification. So when we're writing addition reactions, keep in mind what's happening here is this carbon-carbon double bond. Remember, these are each H's here. So that carbon-carbon double bond will open up. We'll still have two H's on each carbon, but we now have an additional bonding site available on each carbon. So these two chlorines right here can really hop right onto that, to those two available bonding sites. So we would expect to end up with still our two carbon chain we started with. Each of these carbons is now going to have a chlorine on it, and those hydrogens that we had originally will be there as well. In an addition reaction, you're really just adding everything together. If you were adding water to this alkene molecule, 1-propene, or just propene, this really separates itself out into an OH and an H. So your product here would still have your three initial carbons. That first carbon on the left has three hydrogens. Our double bond is gone. Probably this H could end up maybe here. We have our H from before also, right, H's to be consistent here. On our end carbon, we had two H's to start with, and now we're going to add that OH group. Could this possibly end up like this? Absolutely. Those are two very equivalent products. In organic chemistry, if you take that in college, you'll kind of learn which one of those would be more likely to form, but for our purposes right now, either one is possible and equally correct. For substitution reactions, remember what's actually happening here, if you imagine that this is two Cl's attached together, one of them is simply going to switch places with one of these H's. We do end up with two products here. Our first product in this case is going to be our two-carbon chain with those original H's on it. Where one of those H's was, there will now be a Cl. And instead of having Cl2 right here, our other product will now be HCl. So substitution is really just flip-flopping where two things are in a reaction. In this case, and again, what's probably going to do flip-flopping is this H. We're not really going to flip-flop with that H, or this OH, not that H, because we really need to get a different product there. So now we would still have a two-carbon base. We're going to leave our number of H's on the left carbon the same. Two carbons are going to remain, or two hydrogens are going to remain on that carbon. We put that hydroxy group on there. We have this H left over here. And if you imagine that the flip-flop occurred with one of these H's, switcheroo, if you will, our other product now would be H2. Esterifications are a little bit more difficult. They are asked somewhat on part 2, so it is nice to be able to get comfortable with them. In an esterification reaction, we need to identify how many carbons our alcohol has, 1, 2, 3, 4. And how many carbons our acid has, and then how many carbons our alcohol has. So in our ester product, we're going to start by drawing the 4-carbon chain that came from my acid. And I'm going to fill in the H's that I would expect to have on here. This carbon right here gets that double bonded O. The single bonded O. This H, remember, is what's going to get chopped off of here. The two alcohol carbons are going to end up strung onto the end of this molecule. Your other product here, remember, this OH group right here bonded together with this H to form water. You should be able to justify your answer using the law of conservation of mass. So on the left-hand side, I have 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. As far as my number of hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have 1, 2, 3 oxygens on my product side, 1, 2, 3 oxygens on my reactant side. Oops, I'm sorry, I went ahead too fast. So I'm going to scroll down to our other example down here. This example involves fewer carbons, so it should be a little shorter to draw out. I have 3 carbons in my acid. I start by just drawing this simple chain right here, showing where my double bonded O is. And I fill in those remaining H's, they're not going to change. Keep in mind this H is the one that's going to come off. My alcohol has 1 carbon. It will still have 3 hydrogens attached to it. The OH is going to come off, get together with that H from my acid, and we're going to make water. Very often you'll be asked to figure out what's missing in a particular reaction. In an esterification reaction, I usually just kind of start by using the law of conservation of matter here. Also, I can line up like what looks similar. So this particular part of this acid looks like this part of this ester. Knowing what an esterification reaction is really helps me out here because I happen to know that my X product has to be an alcohol. Now, let's say you didn't know that. You're not dead in the water yet, okay? So I've got 1, 2, 3 carbons right here that are represented right here. That tells me in my X, I have to represent those 2 carbons. So I know I'm going to have 2 carbons in that X. Now, as far as my O's go, I have this O and this O. I'm going to cross those guys out. I know now, because I have 1, 2, 3 oxygens on the left side, that I have to have an O somewhere in that product, or somewhere in that reactant. Now I'm going to look at my number of H's. 1, 2, 3, 4, 5, 6. So I have 6 on my reactant side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That means I need to have a total of 6 hydrogens in my missing alcohol. Now, if you don't know this is an alcohol, what you can do at this point is say, okay, I've got to have 2 carbons. Somewhere in there, I've got to fit 6 hydrogens and an oxygen. It's extremely helpful to know that one of these is an OH group. If you just tried to do 6 hydrogens, you'd get a simple alkane like this, okay? And that really takes care of everything but the oxygen. Keep in mind that if on this bond we put in OH, we now have taken care of that oxygen, when we've also kept the same number of hydrogens, so we've balanced that out. In order to have this halide molecule, our X that is our reactant, and again, you can kind of identify that this is going to be an addition reaction. We have to have a reactant that has 2 carbons in it. That reactant also has to have 1, 2, 3, 4, a total of 5 hydrogens over here. Right now we only have 1 hydrogen on the left-hand side. So we have to put 4 hydrogens on here. So you can imagine, and I happen to know this is an alkane, so I'm drawing them at an angle, but even if you didn't, once you put those hydrogens on there, you'd say 1, 2, 3, I better throw a double bond in there. Again, knowing this is an addition reaction will help remind you that I have to have an alkene reactant. Last but not least, this is a substitution reaction. And I'm going to fill in these H's just for the visual here. And remember, this F2 is actually, 2 F's like that. This guy and this guy are going to be switching places. So these are all remaining as H's right here. This one H is going to be in my product over here, and this one F is going to be in my product over here as well. And again, you can go through, you can count these, you can use law of conservation of mass, and that will really help you to figure out what you might be missing. Take another minute and do esters is not a bad idea. Ethanoic acid plus alcohol, ethanol, we may not have done this in lab yet. If we have not, we will. You can see that your acid includes 2 carbons, your alcohol includes 2 carbons, so we have 2 carbons, 2 carbons. And again, that water product, and that ester functional group. So if we imagined we had butanoic acid, so butanoic acid has 4 carbons, plus 1 pentanol, our product here is going to be quite large. We're going to have a total of 9 carbons in it. I'm going to make myself a little more room for this product. Oh, maybe I will, maybe I won't. So I'm going to have 4 carbons coming from my acid. Then I'm going to add that functional group. 5 carbons from my alcohol, and then a whole lot of hydrogens go on here. I need to also take care of this H that was right here, and that OH that allowed that to be strung together, that now we're going to leave in the form of water. Last but not least, we have propanoic acid. And 1 butanol. And you could really choose to show that OH group elsewhere. For example, if you wanted to show it here or here, as long as it's on an end carbon, it doesn't really make any difference. It just has to be on that first carbon on the molecule. So my ester, you can make a nice prediction here, is going to have 3 carbons and 4 carbons. It's going to have a total of 7 surrounding that functional group. On the side that will be attached to the double bonded carbon, we'll have my 3 that came from that original acid. On the other side, I have my other 4. And again, fill in those hydrogens. Our other product here is water. If you can write an esterification reaction and predict the parts of that, you have a nice understanding of several functional groups, and it's a really good showing of your competence with organic.